about encoding complete metric structure by classical structures. Please, Nate, the floor is yours.
Thank you. So first, I'm going to share some slides, and hopefully this works. Can everyone see the full screen? Yes?
Not yet.
Nate, it's dark. The same thing
It's
that
dark.
happened to me earlier.
Okay. Let me
Yeah, now it's fine.
now it's fine. Okay. So let's try. Now, can everyone see the more or less full screen?
Yeah, it's fine.
Okay. So I'll try to stick with it this way. Okay. So thanks, Rohana, for that great introduction. And thanks for the invitation to talk at the seminar. I'm going to be talking about transferring results from infinitary classical model theory to infinitary continuous model theory. So first, we're going to review a little bit about metric structures and continuous logic. Now, before I go into the definition, I want to say just a word or two about continuous logic. I'm not going to go into much of the history, but over the last 15 to 20 years, there's been a consensus that continuous logic is in some sense the right logic to study continuous structures, i.e. structures that are built from metric spaces in various ways. So Banach spaces, complete metric spaces, anything of that form. And it's the correct logic in the sense that lots of classical first order logic lifts into that context in a way that sort of theorems generalize, even if not word for word, but they have analogs in the continuous context. So what is a metric structure? So basically it consists of a bounded metric space, which is the underlying space. This is the analog of the underlying set in a normal classical structure. So we want to think of the truth values as not 0, 1 as in classical structures, but as real numbers, where we think of 0, unlike classically usually corresponding to false, as corresponding to true. And the real number is sort of how far away you are from being true. So with this sort of intuition, a relation is just going to be a non-expanding map from my metric space into the real numbers. Functions are likewise not going to be arbitrary maps, but are going to also be required to be non-expanding, or Lipschitz maps. Now, for those of you who've seen metric structures in continuous logic, you'll note that this is a slightly more restrictive notion than the standard notion, which allows arbitrary, uniformly continuous functions, but restricting to Lipschitz functions will greatly simplify the presentation. But everything in this talk can be made to work in this more general context. Okay, so what is a formula? So now that we defined a structure, we want to sort of be able to talk about what are the analogs of formulas. Well, just as classically formulas are built up from terms, functions, and relations, we have them built up similarly from terms, functions, and relations, but with one new sort of more complicated type of operation. This is connectives. So all relations are formulas. For any two terms, the distance between those two terms is a formula. And we want to think about this as the analog of equality. So we want to think of the distance between two elements as sort of how close they are to being equal in a metric space. And so thinking once again of the real numbers as the truth values in a metric structure, the distance is just how close you are, is the sort of the truth value of how close two elements are to being equal. Then we have the femum of the truth values and the supremum correspond to the quantifiers. And then we have the connectives. And there's sort of two different types of connectives in infinitary logic, continuous logic. So first, if I think of what a connective is classically, it's a map from some finite number of truth values to true false. So for example, conjunction takes two elements, and if and only if both of them are true, does it return true, otherwise it returns false. So in that context, if we're thinking about truth values being real numbers, arbitrary connective should just be a map from some finite power of the real numbers to the real numbers, which is non-expanding. And so that's sort of the first type of connective. However, because we're dealing with infinitary logic, we also want to deal with infinite conjunctions and disjunctions. And here things become a little trickier because we don't want to look at arbitrary maps from reals to the omega, because that's that's a much larger space. So instead, we just look at conjunctions and disjunctions, just like classically, where the conjunction and disjunctions are just the soup and the inf of the collection of formulas. And further, we require all the formulas to have exactly the same free variables. So in this way, we get an analog of L infinity omega for continuous logic. And we have a similar analog for L omega 1 omega, where you just restrict the size of the conjunctions and disjunctions to countable conjunctions and disjunctions. Okay, so I'll quickly walk through this definition, but more or less it's exactly what you think it is. So once you have a formula and you have a structure, you need to define a way to instantiate formulas via structures. And this goes exactly the way you think it would. Terms are instantiated as functions that they sort of correspond to. The distance relation is instantiated as the actual distance function in the metric space. The connective, you just apply the connective to the instantiations of its inputs. Infimum and supremum are interpreted as exactly the same way, and similarly with conjunctions and disjunctions, with, as I said, the conjunctions and disjunctions being the soup and inf of the corresponding formulas you're taking the conjunctions and disjunctions of. Okay, so metric sentences. So now that we have a formula, we need a notion of a sentence. Now, classically, we get sentences by simply quantifying out all free variables. That's not quite what we want to do here, because it's not, because we really want to look at when a formula is equal to 0. So if you remember, we're thinking of 0 as true. So an infinitary metric sentence is just some metric formula with no free variables, and the statement that formula is completely true, i.e. it equals 0. Note these are sometimes called closed conditions. Now, if I have an arbitrary formula that's that has free variables, and I say that equals 0, well, in that case, we're just going to quantify out all the free variables first, and then set it equal to 0, i.e. take the supremum of all the possible values and say that supremum is equal to 0, i.e. for any input, the formula is maximally true. Okay, so this thing gives us a notion of, so now that we have metric sentences, we have sort of a semantics of metric structures. We have the structures, we have the language, and we have formulas, and we have a way to interpret every single formula inside the structure. Okay, so now I want to talk a little bit about what I call cognate metric spaces. Now, the title of the talk is Transferring Theorems from Classical Results to Continuous First-Order Logic. So to do so, we're going to need some way of representing these continuous structures as honest-to-God classical structures. And that's where cognate metric spaces come in. Okay, so as I said at the beginning, over the last decade, maybe 15 years, metric structures have emerged as the correct logic to study objects that arise from analysis or built from continuous objects. And so many continuous structures many classical theorems have continuous analogs. And so the question we'd like to say is we'd like to not have to reprove all of these theorems in a piecemeal basis. We'd like to basically be able to say, here's, a stick, you hit the theorem with a stick and you get the continuous analog. Especially analogs of theorems for L omega 1 omega and L infinity omega. And that's sort of the goal of the talk. And that's what we're going to do now. So let's first consider a test theorem. So the downward Lowenheim-Skolem theorem. So downward Lowenheim-Skolem theorem says that if I have any countable theory of L omega 1 omega, this is the downward Lowenheim-Skolem theorem for L omega 1 omega. And any classical model, then there's a countable substructure which also satisfies the theory. Okay, so this is a really important theorem. It's sort of, in some sense, for the first order case, can be thought of as saying first order logic, the full Lowenheim-Skolem theorem, so sort of first order logic can't really talk about different types of infinity. But it also says that sort of, if I only care about existence of theories, size of the structures in some sense doesn't matter. It sort of is a good way to sort of say, an important part of sort of saying the model theory doesn't depend on the background set theory. All right, so let's give my favorite proof of this theorem. And it follows from the proof for the first order logic case. And the idea is, in particular, the first order logic case also for set theory. So we take a transitive set containing our theory. And then what we do is we say, okay, well, let's take the entire universe and let's take a sigma-1 elementary substructure of the universe containing our transitive set and our model. So we then take the transitive collapse of this sigma-1 elementary substructure, and we get an actual honest-to-God transitive set. And because it's a sigma-1 elementary substructure, every single thing you could more or less want to say is preserved. So our image of our model, it still satisfies the theory because the theory is in this transitive set, the model's in the transitive, the image of the model's in the transitive set. Therefore, it and because it's elementary, sigma-1 elementary substructure, the image of the model must satisfy the theory. Okay, but because it was a countable transitive subset, everything in sight has to be countable. Therefore, our image of our model has to be countable, and we've found a countable model of our theory satisfying, or countable model satisfying our theory. Okay. So now let's look at the same argument, but for continuous structures. All right, well, we start with a transitive set. We start with a sigma-1 elementary substructure of the universe, and we throw in our continuous model. Well, now the problem is that the image of our continuous structure need no longer be a continuous L structure. And the reason for this is that when I sort of take the transitive collapse, it's no longer has to be complete. Because remember, our continuous structures are always complete metric spaces. So the simplest example of this is consider just the real numbers with whatever structure you want on them. Now, when I take my transitive collapse, I get a classical elementary substructure of the real numbers. But no countable elementary substructure of the reals can be a complete metric space that's sort of complete metric space because it's going to contain the rationals. So, so any complete metric space has to have the size continuum. So what's the solution? Well, the solution is we need a different notion of size to make this make sense. And the way we do this is we define what's called the density character of the metric space. So the density character is the minimal size of a dense subset of the metric space. Now, if you remember the problem with the Downward-Lowenheim-Scullum theorem in that context of continuous structures was when we took our transitive collapse of the universe, we were no longer complete. But what we were is we were still a dense subset of the reals. And when we took the completion of that dense subset, we got the reals back. So what the density character is saying is what we really want to look at is just these dense subsets. And we want to sort of think of the dense subsets as containing all the necessary information that you need of the metric structure. And so that's sort of what our goal is going to be. Now, I should mention that independently of this work, Will Boney has also studied encodings of continuous logic via metric structures. His notion is slightly different than mine for technical reasons I can get to afterwards if people are curious. But he was also interested in AECs and other related things, which are sort of, I'm not focused on in this talk. Okay, so, all right, so now that we know what we want to do, we want to sort of figure out how we sort of formalize this idea. All right, so this is where cognate metric spaces come in. So the idea is we want to sort of encode the classical structure, continuous metric spaces via classical structures. Well, the naive thing to do is just to consider a special sort corresponding to the reals, and then just have the distances land in that sort. And then you have your metric space and you have your special sort, and you have your function, which is the distance map, and you get a classical structure in that manner. The problem with that is exactly the problem we had before, is that now all of your structures are forced to be sized the continuum. They're forced to have the reals embedded in them. And so this is a problem because for exactly the same reason is the Down-Scullin theorem failed for the reals. So instead of that, what we want to do is we want to sort of encode our distances as a collection of relations, one for each rational. The idea being that you don't need to know, like that you can sort of pin down the distances by just knowing whether or not, knowing all of the rationals which are above your distance. And so by adding a relation for each rational, basically saying the distance, dq says the distance between x and y is at least q, you can recover the actual distance from that information. And in the process, you have a classical structure which no longer has to contain the reals as part of the structure. And what's more, there's, because you're just taking the, because the infimum of these q is just, can be expressed as a sentence about the various relations, there's a single sentence of L omega 1 omega, which exactly captures the notion of what it means to be a cognate metric space. And the idea is you basically, it's not hard to sort of think about what this is, because you sort of informally define the distance via a formula that's sort of the conjunction of all the distances that hold, and then you write down exactly the metric space axioms, and they translate exactly as you think they would. But the key point here is, it's not just that we've now encoded this via classical structure, but we've been able to sort of cut out all of those structures which are cognate metric spaces by a single sentence of L omega 1 omega. And that's important because L omega 1 omega is absolute, and it will sort of allow us to, with a little more work, lift theorems from about L omega 1 omega to cognate metric spaces. Okay, so now that we've talked about cognate metric spaces, we want to talk about cognate metric structures. So this is where sort of things become interesting. So as I said, we wanted to represent not just a metric space via a classical structure, but an entire metric structure. So this includes all of the maps, all the sort of maps to the reals, this whole sort of ball of wax, all by a single classical structure. Okay, so we now run into another problem. So isomorphism is always, so for those of category theorists out there, you may know the notion of evil, which basically is structures with properties which are not preserved under isomorphism. So if I have some property of anything, call it a metric space, call it a widget, and I move to an isomorphic copy of the object, and that property is not preserved, that property is known as evil. And you don't want that. We don't want that. So one of the problems with this encoding of cognate metric spaces via classical structures is you can find isomorphic cognate metric spaces which correspond to being the same completions. So for example, if we want to think of cognate metric structures as sort of representing their completions, because we want to think of them, because dense sets sort of encode all of the information in a complete metric space, then it's a problem if you have non-isomorphic structures which sort of represent the same structure, because non-isomorphic structures have some property of one that's not of the other. So for example, with Q as a field and Q with pi as a field, both their completions are the reals. So we want to think of them as both representing the reals, but one has a transcendental element and one doesn't. And so that's a problem. So we need some way of getting around this. And the solution is we need to change our notion of map. So classically, an isomorphism is just a map of the underlying set which preserves all of the relations and all of the structure. And that's too restrictive because, as we saw, there are non-isomorphic structures which we want to think of as the same. So how do we do this? Well, the intuitive idea is, if I think about what's going on here, is I have two dense sets and I want to sort of describe a map between their completions. Well, the first part, if I have, say, call them M and N. Well, a map from a dense subset to any complete metric space extends uniquely to a map from the completion of the domain to the completion of the range. So really, we only have to worry about mapping the dense subset of the domain to the range. But if I have a dense subset of the domain and a dense subset of the range, there's no reason that the image of the domain has to hit my dense subset of the range. It might hit things that are in the completion. So we need some way of describing the image of points in the domain using just the dense subset of the range. And the way we do this is we say, okay, well, every point in the range can be completely described by a Cauchy sequence moving towards that point. So what we really need to do is we really need to just identify the distance of the image of, let's call it X, to every dense point in my range. So I have my X and M, and I want to look at f of X. And the information I need is just the distance from f of X to every other point in my dense set. Now, f of X may not be in my dense set, but if I can identify all those distances, I can identify f of X in the completion of the dense set. Okay, so that's what's going on here, is we're going to define a series of relations, just like we did with the distance function, which we want to think of as saying, as sort of saying the distance between f of X and Y is no more than Q. And I'll briefly go through them. If distance is no more than Q or no more than P, and Q is bigger than P, it's not going to be any more than Q. Right. Q is bigger than P. Then we also have that for every P, there's some point. So whose distance is no more than P. So it actually is in the completion. And then we have these last two, which are a little technical, but basically correspond to the analogs of the triangle inequality. Okay, so this is what we want to know. We want to define as the notion of a map. Now, a quick sidebar for, I don't know how many category theorists there are in the audience, but if you're aware of the notion of a distributor or a profunctor, this is essentially what this is capturing. So there's a way to think about complete metric spaces as enriched categories. And under that notion, there's a categorical notion of Cauchy completeness. And what you have is you have a notion of a profunctor, which very roughly can be thought of as if I have, category A, category B, a profunctor is a way to sort of merge them together to make a single category out of all of them. And those profunctors also sort of exactly correspond to maps of the completions between the metric spaces. That's not obvious. It requires some work. If you know the terms, then this will make perfect sense. If you don't worry too much about it. However, it is, in my opinion, very cool. Okay. So now we have, one of the most important theorems that makes this whole thing work is that the category of cognate metric spaces and cognate structure, so that's next slide. We have that given any cognate metric spaces and any map between them, there's a unique Lipschitz function from M to the completion of N, such that the distance between f of X and Y is less than P, if and only if the actual distance between f of X and Y is P. So these notions exactly capture what we were trying to do, that we're sort of trying to pin down the distance between the image of F and every single element in our dense subset of the codomain. So in particular, what this means is the category of metric spaces with cognate metric maps is equivalent to the category of complete metric spaces with Lipschitz maps. So in some sense, these are the same objects. They're just they're cryptomorphic. These are two different ways of capturing the same concept. Okay. So in particular, for every metric space, we can associate a cognate metric L structure, where basically the idea is a metric L structure consists of a metric space along with a collection of maps between arities. So, M to the 5 to M to the 1, along with maps from our metric space into the rationals. So now that we have a notion of map, which exactly captures Lipschitz maps, we can define a cognate metric L structure as just a cognate metric space along with corresponding cognate metric maps for every relation and for every function. And by the equivalence of categories, these are going to sort of correspond exactly to continuous metric L structures. Okay. So this is the basic background, is we've sort of, we now have a way to encode metric L structures via classical structures in a way that sort of behaves the way we want it to. But that's not sort of all we want to do. What we also want to do is we also want to transfer results from infinitary logic into continuous infinitary logic. So what we want is we want an actual theory of cognate metric maps. We want to be able to sort of describe by a sentence of L omega 1 omega what a cognate metric map is. So we have this encoding of cognate metric structures, but we want to be able to sort of identify those models of that language which actually are cognate metric structures. And we want to be able to do so in a way that only requires L omega 1 omega. Right. And in order to do this, we need to be able to sort of identify when we have a map, when basically we have a collection of relations which sort of corresponds to a cognate metric map. And it's not that hard. We sort of we had the axioms of a cognate metric map earlier on, which I will quickly go back to right here. And if you think about these, all of these can be expressed in terms of sentences of L omega 1 omega. So because of that, we have a single sentence of L omega 1 omega which captures a cognate metric map. And in particular, this allows us to do the following. So now that we have cognate metric maps, we can also talk about the basic operations on these metric maps. So if you remember, the way we built formulas up was we said, okay, well, first I can build terms by composing functions. Well, if I know what it means to be a cognate metric map, it's not hard to say what it means for one metric map to be the composition of two others. Likewise, if I have a connective, which is just a cognate metric map from the reals to the reals, I can compose that with my formulas. And I can identify via a sentence of L omega 1 omega what it means for one metric map to be the composition of a connective with another cognate metric map. And lastly, supremum and infimum can also be expressed. I can say in a sentence of L omega 1 omega what it means for one cognate metric map to be the supremum of the arguments of another. That requires a little bit of work, but it's not that hard. Okay, so what this means then is we have not just a way to translate continuous L structures into cognate metric L structures, but we have a way to actually lift sentences of continuous infinitary continuous logic into classical infinitary logic. In other words, for every, so we're going to assume we work with moralized theories, but you can do it without them with a little bit of work. For every continuous moralized theory T, there's a classical theory T star, which contains the statement that all of its models are cognate L structures, such that a metric structure satisfies the theory if and only if the corresponding cognate metric structure satisfies the classical theory. So in this way, we have a way to translate continuous theories into classical theories. And therefore, we can use this to show that any theorem or many theorems that are true about classical theories will also be true about continuous theories. Okay, so what are some of the results we can say? So and I'll go through sort of make these statements a little more precise in a second, but the following all have continuous analogs. So the Down-Lowenholm-Scullin theorem. So if you remember, this was the test case. This was the case that we wanted to have, where we wanted to sort of talk about, well, how does it, so that's going to have an analog in the continuous logic that immediately lifts from the corresponding analog for classical L omega 1 omega. Similarly, the Hanf number for continuous logic. So if you remember, the Hanf number is the number such that if you have a model of that size, you have to have models of arbitrarily large size. There's a nice easy result that shows that any logic with only a set number of formulas has to have a Hanf number. And it's well known that the Hanf number for classical logic or classical L omega 1 omega is Beth of omega 1. And by this transfer result, we also have the Hanf number for continuous logic will also be Beth omega 1. We're also going to have an analog of Morley's two cardinal theorem, analog of Barway's compactness, and an analog of Barway's completeness, all for continuous structures. Okay, so let's state these theorems precisely. And I'll talk a little bit about the Lowenheim-Scullin theorem because that'll hopefully clarify how these things work. So the analog of the Lowenheim-Scullin theorem says that if T is in L kappa omega and it's a continuous theory, and M satisfies the theory, and M is a metric L structure, then there is a metric L structure contained in N such that N also satisfies the theory, and N has density character at most the size of the language plus kappa. So how do we prove this? Well, we take our continuous structure M and we translate it into a cognate metric structure, C of M. And now we take our theory T and we translate it into the corresponding T star, the classical analog of the continuous theory. Now we apply the downward Lowenheim-Scullin theorem to our cognate version of M and our cognate version of T. And we get an actual honest to God substructure of M of size kappa. Now that substructure is going to be a cognate metric space and it's going to satisfy our T star. Therefore, the continuous structure that corresponds to it, which comes from the completion, has to satisfy T. So what ends up happening is, so we have some continuous substructure of M, which is just the completion of this elementary substructure, which has to satisfy T because this corresponding cognate substructure satisfies T star. And so that's the general way that you sort of transfer these results is you take your theory, you move to the cognate version, which is in L infinity omega. You take out your structure, move to the cognate metric space version, which is a classical structure. Then you apply the classical version, and then you move back to the continuous land, and the classical version holds. Okay, so for example, the Hanf number, to be precise, is given a continuous language, a countable continuous language, and a theory in L omega 1 omega of that continuous language. There's a if there's a model of density character Beth omega 1, then T has continuous models of all density characters. Now, if you remember, the Hanf number only technically says that you have arbitrarily large sizes, but because we have a downward Lowenheim-Scullin theorem, if you have arbitrarily large sizes, you have all sizes. So Morley's two cardinal theorem. So we say continuous language with a distinguished sort U is a kappa lambda structure if M has density character kappa and U has density character lambda. So classically, there's we have Morley's two cardinal theorem, which says the classical analog of this. So that if I have a classical continuous structure or classical structure in a sentence of L omega 1 omega, and for all alpha less than omega 1, there's a kappa structure of size Beth alpha kappa kappa that satisfies T, then for all cardinals, you have some structure of size gamma where your distinguished subset is only countable. And likewise, we have the similar sort of thing for the continuous version, but where instead of looking at size, we look at density character. Okay, so likewise, we have a Barway's compactness theorem. So if we have any admissible set and we have any theory T in continuous logic, which is sigma 1 definable over the admissible set, such that for every subset of T contained in A, there's a metric structure which satisfies T, then there's a metric structure which satisfies, or C0, there's a metric structure which satisfies the complete theory. So an exact analog of Barway's compactness, but for continuous structures. I might note that that's a little less obvious than you might think because we're looking at countable admissible sets, but we're looking at structures of size continuum. So you sort of, this allows you to sort of talk about this, find a Barway's compactness theorem, even though on its face, continuous structures are sort of too large to consider. And likewise, we have a Barre's completeness theorem. So if L is a countable continuous language and there's an admissible set that contains L as an element, then the collection of sentences which hold in all continuous L structures is going to be sigma 1 definable over that admissible set. Okay. So thank you. With the talk. So
thank you very much, Nate. Okay, we have at least 30 minutes for questions. Please type questions in the chat or just question sign so I can see you want to ask the question. No? Well, Ned, when people think I can also ask a very simple
sure.
question. The beginning was about continuous
Yes.
Logic. I was not familiar with. What is motivation to to represent truth values as an open interval? Why not normalize it? Say to have something like 0, 1, say definite true, definite false, and things.
You can, and you can, and there's not a whole lot of difference. So the reason is because very often what happens is you have metric spaces where you want the distances just naturally to be arbitrary, to be able to take arbitrarily large values. Now you can always normalize this by taking some function and mapping it into 0, 1, and then more or less everything happens the way you want it to. But it sort of it's a formalization that you have to do, which you don't always want to have to do, because it's the things that you sort of arise in nature aren't always bounded. But there's no real harm in doing that for the most part.
Thank you. Yes, please, the audience. Yeah.
Yes. She always has to be part of every talk I give.
Yeah. If we really don't have more questions, then thank you very much.
Okay, thank you.
Nate, thank you very much. And see you again on Logic Universalis webinars. Thank you. Thank you, Nate, and everybody. And see you later.
Very much. Bye-bye.
Bye-bye. Thank you, Ruhana.
Thank you. Pleasure.